So, you remember that we were talking about trying to make graphene topological, that is whether it can act as a topological insulator, and one of the reasons for the suspicion was that it has an unconventional Berry phase, that is when the electrons go around the Dirac points, they pick up a phase which is pi in a closed orbit around the Dirac points k or the k prime points, and also these the sense of rotation is different in the k and the k prime points. Okay, so in one of the Dirac points, say k, it rotates clockwise, and in the other Dirac point it rotates anti-clockwise. So this is said that there is a topological charge that is associated with the electrons in graphenes, which has a value +1 and -1, which are related to these Berry phase of pi and minus pi. And we wanted to sort of understand if there is a definitive way that that graphene can be made a topological insulator, and it turns out that if you add a mass term, that is if you add a term which looks like mi sigma z, it simply sort of shifts the energy levels. There is of course a gap that opens up at the Dirac points, and however that gap is a trivial gap. And why it's called a trivial gap, let's see that. So we have just plotted the band structure of Semenov insulator in this E versus K plot, and it's plotted over the Brillouin zone from the gamma point to K point, M point, K prime point, and so on. And these if you remember, these K and the K prime points are the Dirac points, and you see that there is a gap that opens up of magnitude 2 mi at both the Dirac points. Okay, this is of course an insulator. Now the question is that whether it's a topological insulator, which means the boundaries of the system behave any differently than the bulk, and for that we have resorted to a second approach, which is by breaking the time reversal symmetry in graphene by introducing a complex next nearest neighbor hopping. So that's why we call it as NNN hopping, and this is called as a Haldane insulator, or it is also a named Chern insulator because of the reason that you see there is this plot here where the Chern number is plotted in the phase or the parameter space defined by this capital M and phi. So capital M is nothing but the Mi that we have written in the last slide, and phi is the flux related to the Haldane flux, and this is the flux that appears here. Okay, so that phi is here. So which means that there are these second neighbor hoppings that you see are associated, they are complex second neighbor hopping, which are like T2 e to the power I phi, and the sense of the hopping, like this one is an anti-clockwise hopping that you see here. Let's call it as 1, and let's call it as 2 and 3 and 4 and 5 and 6. Okay, these hoppings are all anti-clockwise hopping, and these anti-clockwise hopping comes with a they all come with a sort of sign which is opposite to that of the clockwise hoppings, and so on. Okay, and if you want to make this these hoppings among the next nearest neighbors to be purely imaginary, you can take phi to be equal to pi by 2, because your T2 exponential I phi for T2 phi equal to pi by 2 becomes equal to T2 e to the power I pi by 2, which is nothing but equal to IT2. Okay, so it is either IT2 or it's minus IT2 depending on the clockwise hopping or the anti-clockwise hopping, and that's the scenario that Haldane considered, which could in principle make graphene to be topological. And I just want to remind you that this was actually told by Haldane in 1988, which is much ahead of the discovery of graphene. So it was purely a honeycomb lattice in which such a thing has been thought of, and then it would be giving rise to a topological insulating property to this, which is evident from this plot that's in the right bottom part of this. There is a Chern number phase diagram. We'll come to that in some time. Okay. So, let us take this Haldane suggestion and see that what it gives rise to, whether we can understand a model, or rather we can write down the Hamiltonian that comes out and write it down in K space and see the how the low energy behavior or the low energy properties of that model and so on, and then really assess that whether that gives rise to a topological insulator. Okay. So, this Haldane term, so we write Haldane model. Okay. And the model is written as, let us write it as H H, this is equal to a T2, and then there is a sum over. Now, just to make sure that we are talking about second neighbor hopping, so we write it with a double bracket and I and k, and exponential I nu I k phi and a c I dagger c k plus a Hermitian conjugate. Okay. So, that is the Haldane term, and of course, there are these nearest neighbor tight binding term that is there, and as well if one wants to consider the Semenoff term, that is mi sigma z, that also is there. We will deal with all of them just in a while, but just this is just the Haldane model in which he proposed that there is second neighbor hopping. So, these are hopping of electrons between next neighboring site, not the neighboring site, next neighboring site, and there is a, it is a complex hopping, and that is why it is represented by this phase, and this amplitude is T2 and the phase is given by this, and there is also a nu k I equal to minus nu I k is same as minus of nu k I, that gives you the chirality. Chirality means the sign change as one considers clockwise hopping and anti-clockwise hopping. Okay. And in this particular case, Haldane considered phi to be equal to pi by 2, such that the hopping becomes completely complex, and then it is written as I T2, and this is equal to sum over I k. Just to remind you that this double bracket is to ensure that we are talking about second neighbor and not the nearest neighbor. So, this would mean nearest neighbor hopping, and this would mean next nearest neighbor hopping. Okay. This is the usual convention that is followed, and this is equal to nu I k c I dagger c k plus Hermitian conjugate. We have been writing the Hamiltonians, all of them that have been previously discussed by these in the second quantized notation, and one should get familiar with this. This means that there has been an electron or a particle that is annihilated at k, that is site index k, and is been created at I, which means that there is a hopping that has taken place, or there is a transfer of that particle or the electron that had taken place. Okay. So, this is the Haldane Hamiltonian, and we will do a Fourier transform of that, just to make sure that we are not forgetting the total Hamiltonian. So, the total Hamiltonian, let us write it as some h, okay, we can write it as k, or we write it initially without referring to whether we are writing in k space or in real space. So, this is the tight binding term, and then there is a mi sigma z term, which is the Semenoff term, and then there is this h Haldane, which is denoted by HH. Okay. So, this is the total Hamiltonian that one has to solve in order to get the energy spectrum and assess that whether there is a topological behavior, that is the bulk of the material behaves differently than the edges. We will come to this in a while. Just a priori, since we are talking about edges and the bulk, we cannot be talking about systems which are infinite in both the directions. Okay. So, we will have to consider finite systems which will be called as ribbons, which we will just take in a moment. Okay. So, consider this Hamiltonian, and you do a Fourier transform of this Hamiltonian. And how you Fourier transform is you can do that. You can write this H of k. This is of course this is written, equation 1 is written in the, okay, let me make this as equation 1 and this as equation 2. Equation 2 is in the real space. So this k is not wave vector, but it's a site index. However, this k when I write it with a vector, that's a momentum or the wave vector that we are referring to. So this is just a step that I'm skipping. You should fill it up. This is equal to a minus T2 and then the sum over k and twice of sine of k dot A1. I'll show you what A1 and A2 are. Sine of k dot A2 and minus sine of k. So this is a k dot A1 minus A2. So this is your the k part of the Hamiltonian, and this is ck up dagger ckA and a minus ckb down dagger ckb, and this is the operator part of it, and this is the coefficient. The one that's in the square bracket is the coefficient which comes because of the Fourier transform. All right. And what are these A's and A1s and A2? So let me draw this unit cell of graphene, and this is equal to, so okay, so this is your A1 and this is your A2. Okay. So these are called as the direct lattice vectors, and they also connect the next nearest neighbors. So A1 is written as A by 2 3x cap plus root 3 y cap, and A2 is written as A2 3x cap minus root 3 y cap. Okay. So these are the vectors, the direct lattice vectors which are written here, and these k vectors are the two-dimensional wave vectors in the plane, and so this is kx and ky. Okay, and A1 and A2. So everything is defined, and just to make sure that this is a hopping that is diagonal in the sublattice basis, your sigma denotes the sublattice degrees of freedom. It goes from a sublattice to a sublattice and a B to a B, and as you see that these are the red ones are the one type of sublattice, say for example A sublattice, and this blue ones are the B sublattice. So now you see the dotted lines denote hopping from A to A or B to B, and that's why you have this as the term that that we find it here. Okay. And so now what we need to do is that we of course can plot this Hamiltonian by just solving all the terms, that is including a tight binding and a mi sigma z, and this term we can put it in a 2 by 2 form, and it will come in the form of a d dot sigma, and we can plot the eigenvalues, or and find out the eigenvectors of that Hamiltonian, which we'll anyway do. But before that, we let's do the analytic things of finding the low energy part of the dispersion by expanding around the k points, and I showed you here that these are the k points which, in the absence of these complex second neighbor hopping, they are touching linearly like this. Okay. Now, as you give this this term, which is mi sigma z here, they become like this. Okay, and slight bit of sort of curvature that comes here, which is so it is like this, and of course as you see that it's slightly quadratic there, and so this is the gap that we wanted to open up. But at the same time, we also have in mind that it's just not opening up of a gap, but it's something more than that, and let's see that how we arrive at something more than that. Okay, so let's write down the low energy Haldane model. Haldane Hamiltonian or Haldane model. Okay. So, low energy means that we will take this q vector and expand it around these Dirac points. Okay. So, this k is the wave vector of the electrons and this is a Dirac point. So, this can be k or k prime, and so this is it could be as well a k prime, and whenever I denote a Dirac point I write it a little bigger so that you understand that this is not the variable k vector. Okay. So, if you want to write this down, then we can write this as the low energy part or rather let me just do some simplification. So, this is equal to k and there is a h of kz and a sigma z, and then of course the term that is there, that is that c k a up dagger c k and so on. Now, that part is taken into account in the z sigma z thing, that is the b comes with a negative sign here, and this h of k is nothing but that is the z component of the d vector, which we have been talking about for quite some time. So, it is 2t2 and a sine of k dot a1 minus sine of k dot a2 and minus sine of k dot a1 minus a2. I have defined a1, a2 and k, all everything there. Now, this is that h of k, and what you do is that if you expand around the k points, we can write down h of q and which is equal to some about those Dirac points, which are we will just call them as 0 for the moment and do a Taylor expansion about these Dirac points. So, this is the first term in the Taylor expansion, which is a constant, and the other terms are like this 2t2, and now I will just take the small wave vector, which now we write it as q. So, it is a qx x cap plus a qy y cap. This k has been expanded around the Dirac points, and then dotted with a by 2 and 3x cap plus root 3 y cap. You should do it a little more carefully, that is write down the exact k points. You can do it k or k prime points, it does not matter, but you should write down the coordinate of the k point, which we have shown how to calculate, and then do the expansion, the Taylor expansion about that. Then you will get exact factors which will finally write it. Okay, so I am just simply writing sine, as you know that sine of x equal to x for small x. Okay, and this is what we have been applying here. So, this is that, and then you have a qx x cap plus a qy y cap dotted with a by 2 and a 3x cap minus root 3 y cap and minus a qx x cap plus a qy y cap and dotted with 3x cap plus root 3 y cap, and this is a1 minus a2. So, 3x cap plus root 3 y cap, and if you do this open up the bracket, you will have nothing left here, which means that you can see this carefully that qx into 3 will become 3qx, and there will be a root over 3 qy, and there will be a minus 3qx which will get cancelled and so on, and there will be so this anyway cancels. So, there will be a 2 root 3 ky and this 2 root 3 qy will come from this other two terms. So, this is this whole thing becomes equal to 0, and you are left with a constant term, constant, which is h at the Dirac points, and when you calculate that, this constant will have some value, and that tells you that the low energy dispersion of the Haldane model does not disperse, which means that it has no q dependence, it is independent of q. Okay, so this is the low energy form for that, and one can write down the Haldane Hamiltonian, which is as mh sigma z gamma z. Okay, gamma z once again denote the Valley degree of freedom, and sigma z is of course the sublattice degree of freedom. Okay. And so this mh is the Haldane mass, and it has a value, as I said, that you have to do it carefully in order to get this particular value or this constant, and this comes out as 3 root 3 T2. Okay. In some literature you will find it a minus 3 root 3 T2, but it does not matter. I mean, this is the magnitude of the Haldane term. So, just to understand what is this mh or what is the Haldane term, just like in the Semenoff you got a mi, and here you get a mh, which is because of this Haldane, the mass, and that depends on the second neighbor hopping amplitude T2. Okay. And it has of course different signs at the different sublattices, which means at a sublattice it is equal to plus 3 root 3 T2, and at the other sublattice it becomes equal to minus 3 root 3 T2, and so on and so forth. Okay. So, the total Hamiltonian, we have worked out earlier the Hamiltonian corresponding to the tight binding part as well as the Semenoff part. When I say the Semenoff part, what I mean is that you simply try to put two different masses, that is the same magnitude but different signs at the two sublattices, and hope that that opens up a gap. Of course it does, but that gap makes it an insulator and not a topological insulator. Okay. What it means is that the bulk of the material, or inside of the material, inside of a a graphene sheet, which we will call it as a ribbon, that behaves in the same way as the edges, that is, the edge has no different behavior than the bulk, and that is not called a topological insulator. It is like an ordinary insulator. Only when the edges have conducting modes or conducting states, that is called as a topological insulator, and this is what has been elaborately discussed in the context of quantum Hall effect. Okay. So, I now combine all the three terms and write down this H of Q. This is equal to a H cross of Vf, and then a Qx sigma x gamma z plus a Qy sigma y, and now I combine both these terms because both of them are like they have a sigma z term, excepting that one has a extra gamma z, which the Semenoff term does not have, and so we will write this as so this is the total low energy dispersion, or low energy dispersion for the total Hamiltonian. This we have already seen this part. So, this is tight binding, and this is effects of breaking time reversal symmetry. And m tilde is nothing but mi gamma z. What it means is that m tilde has a value mi plus mh at k, that is at one of the Dirac points, and this has another sign at the other Dirac point. Okay. So, these both are Dirac points. Okay. So, it has two different signs, which means that the magnitude of the gap is not identical at both the Dirac points, and they kind of differ by this. Okay. So, if you look at the spectrum for the Haldane model, then it looks like this. This is numerically calculated for this Hamiltonian that we have written down here, rather here. But then for analytic purpose, we have done a Taylor expansion of the Hamiltonian at low k, and this is how you get this thing. Now again you see that there is a gap. So there is a gap here. Okay, I mean, I'm sorry, I did not mean to touch that, but then it may not be very visible to that. These gap and this gap are not the same. They should not be, unless while generating these plots I have taken mi to be equal to 0. So in any case, what it means is that the gap will at this one of the k points will be like mi plus mh, and this will be like mi minus mh. This is what it should be. So there will be a little tilted on one side, and that is what will give you the dispersion. Now if you consider this dispersion, it's written as electronic spectrum for the Haldane, or it's called as a Chern insulator, and Chern insulator, the name has been coined because the Chern number is not 0 and it's an insulator, and it's a topological insulator. You see that the band structure doesn't look any different, and the band structure is absolutely identical. There is a gap at the Fermi level, no matter what the magnitude of the gap is, okay, and that is exactly the same here as well. You have a gap, and this gap has opened up. Is this topological? That's the question that we ask. Is this model topological? That's the question. And how do we confirm if it is topological? Because here, as opposed to the other case where you have just introduced a mass term, here you have broken the time reversal symmetry. Okay, and in order to answer this question, you sort of draw a finite size ribbon. Now I want to sort of spend 1 or 2 minutes here trying to make you understand that if you want to see how the edges are different as compared to the bulk, you have to bring in the concept of edges. Now that means that you cannot talk about an infinite system in both the directions. Okay, it is certainly not an infinite system. It cannot be an infinite system, and it's now one can do one simplification here. Instead of taking a sort of finite system in both the directions, one is entitled to take a finite size only in the y direction. So this the y direction has been shown, and in the x direction it is infinite. So x direction the ribbon is infinite, and it's called as a ribbon or a nano ribbon, depending on what is the size of the ribbon, is infinite. And in y direction the ribbon is finite. Now if that is the case, you can take the size in the y direction to be like as if the edge modes that will appear on the top edge doesn't interact with the one that appears at the bottom edge, which means they are at least sufficiently far apart. May not be infinity, but and it depends upon your computational skills, and I mean the power that you have, which would be scaling with the system size in the y direction. So more you have a number of atoms and number of unit cells in the y direction, you will have more and more number of I mean the Hamiltonian size will go up, and it will take longer time to solve the problem. But nevertheless, I mean you can take something around 12 to 14 unit cells or 40 to 50 unit cells in the y direction, and that should be good enough in order to calculate these quantities or to see the existence of the edge modes in the system for this particular system, that is the Haldane model, but it does not exist for the Semenoff insulator, and we'll show that. Okay, a little bit of work has to be done, and this is it's numerical work, but you need to understand how the numerics is done, because the numerics by itself cannot solve the problem. You'll have to code things, you'll have to give it in the computer so that it's able to solve. And let me take a sort of a strip in the y direction, and as I said that the y direction will decide, the length in the y direction will decide the size of the Hamiltonian and hence the time to solve the problem. So we have taken a small strip in the y direction and try to sort of consider a tuple. Let's see what a tuple means. A tuple means that you see this A1 and a B1 and a B2 here and a A2 here. So this will called as a, say, a tuple. Okay, and so this red will have 3 neighbors, not this red, but say this red will have 3 neighbors which are B2 here, B3 here and something here. Okay, so these are, because that's at the edge, we have to leave that. But suppose at this moment we are thinking that there is some other atom there, but the presence of edge is important, that you have to realize. Okay, so we'll talk about this as n equal to 1 and this as maybe n equal to 2 and so on and so forth, and then write down the equation of motion, which is nothing but writing down the Schrodinger equation H psi equal to E psi for a sort of given real space problem such as this. Okay, so we write things here. So the tuples are n equal to 1. Okay, so in this tuple there are 3 neighbors, and let's call them as 1a 0. 1 will correspond to n equal to 1, and this a will correspond to a sublattice, and 2a again n equal to 2 and a, and then this is equal to 1a and a delta. Okay, when I say 0, it means the same tuple, which means that this hopping from, say, for example, this red A1 here to this, that's the same tuple, and so on. And then once when you go to the next tuple, you talk about n equal to 2 and things like that. Okay, and this delta is basically the, you go out of the tuple and is the next the unit cell that you have. So there are 2 in the same tuple, that is same n value and not n value, but the same unit cell, and then one connecting to the other unit cell. So here 1 and 2 denote the value of n. Okay, so we want to write down the equation of motion. Now while doing that, we sort of resort to a simplification, because otherwise it will become too big to write in the class and by hand. We'll only talk about the nearest neighbor hopping. Okay, but in Haldane model, do remember that there are this second neighbor hopping. The principle is just the same, excepting that you have more things to worry about, that is more hoppings and more terms to worry about. The size of the system will of course go up, and this is for one tuple connecting to the nearest one. If you have such many such things, the Hamiltonian will be a little big, but that has to be done anyway using a computer. So writing down the equation of motion, so this E B1, that's E psi, which is H psi is 8 T A1 plus a T A2. A1 and A2 are amplitudes of corresponding to the A sublattice for n equal to 1 and n equal to 2. And there are 3 neighbors, the The last one is exponential minus I kx delta. One thing I missed saying that here ky is not a good quantum number. And we'll deal with the system along the y direction in real space, but since this is infinite in the x direction, kx is a good quantum number. Now, this is little strange that you have a two-dimensional wave vector, you take one of them to be a good quantum number, that's you express the wave function in terms of kx, but not in terms of ky, because there is nothing like a ky. So, ky, there is no periodicity in the y direction, so you can't define a ky. So, we will write down the Hamiltonian in the real space corresponding to the y direction, and that is why the size of the Hamiltonian will depend upon how many unit cells we are considering in the y direction. Okay. So, this is one of them, and this is like E A2 is equal to T B1 plus a T B2 plus a T B2 e to the power minus I kx delta E B2 is equal to T A3. Now, we have to go from n equal to 1 to n equal to 1 and n equal to 2, and then we have to go to n equal to 3 plus a T A2 plus a T A2 e to the power I kx delta. As I told that kx continues to be a good quantum number, but there is no ky. So, it is only the parallel wave vector is important. So, E B A1 is equal to T B1 plus a T B1 e to the power I kx delta. Okay. So, you see that there are 2 minus kx I kx delta and 2 plus I kx delta and so on. So, we can now form a matrix corresponding to this. And the matrix will look like, we will write it in the A1, B1, A2, B2 basis, and A1, B1, A2, B2, and so there is 0 here, and then there is alpha star. I will tell you what alpha is. So, alpha is equal to T 1 plus exponential I kx delta, and so this is equal to 0 0 alpha 0 T 0. So, alpha is just the small shorthand notation for the exponential term, the term that is there with the exponential. Okay. So, 0 T 0 alpha and 0 0 alpha star and 0. So, you can diagonalize this matrix for just one tuple that we have considered, and then can find out the eigenvalues and eigenvectors. Now, you do it for as many of them as you want, and then solve the problem in the real space. Okay. So, this is the general scheme of finding out the edge characteristics of graphene nanoribbon. This can be done for a square lattice nanoribbon and so on. I am not saying this is the only way to do it. There are other ways such as the Green's function method, etc., which I do not want to go into, but this method itself is quite powerful in finding out the edge characteristics of a ribbon. Okay. So, I write down the edge states of a Semenoff insulator by writing. So, this k is that you see is kx, that is which in direction that there is a translational invariance, and you see that there is a mi term there, the last term corresponding to the A sublattice, and there is a minus mi term corresponding to the B sublattice, and so on. These are compact forms of writing down that 4×4 equation, which I just showed you here. So, this 4×4 equation or 4 coupled equations. So, this is that. So, for the Semenoff insulator, and if you write it down for the Haldane model, it has this form, and where of course you can put phi equal to pi by 2. This is what we have committed ourselves to, and you see that there is a T2 and there is a T2 and so on, and again k refers to the kx wave vector. Okay. So, these are the amplitudes. So, this is like writing down, so a k n of course refers to that unit cell index that I said, and a b k n. So, this is the two equations, the two coupled equations that will give rise to the amplitudes of the wave function at the a and b sublattices. Okay. And if you plot them, this is for the Semenoff insulator, that is where Mi, there is a term Mi corresponding to plus Mi for the A sublattice and minus Mi for the B sublattice. You see that there is a bulk gap everywhere, and there are this edge mode actually splits from the bulk and goes to as a function of kx. So, this is root 3 kxa. Kxa is just to make it dimensionless, and the root 3 is just added for convenience in order to plot. It's easier to plot it with root 3 kxa rather than just kx. And you see that the Fermi energy is denoted by the red line, red dash dot line, and there is a gap everywhere in a narrow ribbon. Okay. So, this is a calculation for a nano ribbon. And there is a gap everywhere and there are no edge modes, and this is what is expected. And so, Semenoff insulator is not a topological insulator. Okay. So, this is what the story comes out, that just by putting a mass term one cannot get a topological insulator, but now you see the Haldane model, there is a bulk gap. So, this is the bulk, and so this bulk valence band and this is bulk conduction band. Okay. And you see that there are two modes, that these are like getting split from the bulk and they are crossing the Fermi energy, which will give rise to conductivity. And that is why topological insulators are interesting, because of their edge property. You see the bulk behaves differently than the edges. Bulk has an insulating property, whereas the edges have this conducting property. And what we have done is that we have calculated the chirality of the electron, or the sense of motion of the electrons at the 2 points U point and the V point, and it can be seen that at the U point the electron moves from the right to the left, okay, whereas at the point V it moves from left to right. So, they have opposite chirality, and this is what I had been told earlier, that even in a quantum Hall sample, if you remember that the electrons actually move in this direction for one edge and in the other direction for the other edge, and the two edges are far apart, that there is no the possibility that they would change sides. It's like highways in which the cars move. The left lane is for the ones that are going from the bottom to up there, or in this direction, and this will go in this on the other side of the highway, they will go in the opposite direction. And this is what makes Haldane model so a topological insulator. And this is what was expected. In fact, we wanted to find that one can make graphene by adding some terms. It's not only adding some terms, it's like destroying certain symmetries. By destroying certain symmetry, we can make graphene to be acting as if it's like a quantum Hall sample. Okay? So, graphene indeed can act like a quantum Hall. Okay, and well, I mean, this is the main motive behind this, and we are yet not done with this because we have to understand. We of course have gotten one very good instinct that that there are edge modes in the system. The bulk behaves differently than the edges. Now we have to calculate a topological invariant, which is the Chern number here, because there is a time reversal symmetry being broken, and this will give rise to the Chern number phase diagram, which is what will be discussed in the next class. So we just want to wrap up saying that it has prospects, graphene has prospects to be used as a topological insulator if one can have such terms that break the time reversal symmetry, or these can be sometimes these Haldane terms, that is a second neighbor complex hopping, is referred to as the intrinsic spin orbit coupling. So if there are such spin orbit couplings which are strong, then graphene can be used as a topological insulators with such properties. We'll see the phase diagram next. Thank you.